Hi, today we're going to look at concepts and techniques for resource management. I'm Salim Virji, a site reliability engineer with Google. I've been a part of Google's SRE teams working on systems including distributed compute, storage, and consensus. I've also looked into ways for making efficient machine learning systems, not at the tools such as algorithms or compilers, rather how we can develop efficient production environments for machine learning. Today, we're going to take a look at the what, why, and how of understanding the money that you spend on hardware resources. Now, hardware is typically available in shared resources. You're familiar with memory, network, processors, and storage. So we're going to look at the what, the physical resources that are essential to the hardware and services that we build. And we're going to develop an understanding of these because this becomes critical as our systems grow. And that's in part because of the monetary cost of building out all and maintaining all of this hardware. And ultimately, you'll understand that even if you don't work directly with hardware, well, you do, because that's the why. No matter how virtualized your system is, the software and services that you write rely on processors, memory, network, and disk. Yes, indeed, somewhere down that stack, you will rely on a disk. So let's dive into how you can understand the resources that you're using and justify this use to yourself and possibly also to the people who are signing checks for these resources. And there's also the why. Why does the business want to put money into these resources? And finally, we'll use the concepts that we develop to come up with elementary guidance on how to make effective changes in your system and when to know that a change isn't worthwhile. We'll figure out how you can understand priorities and apply them. Because, after all, as systems evolve and scale, we want and need to manage their cost. We're going to use this image server as our example. And this server comes from a tutorial on the Google SRE website. And it's all about a system that serves images of cats to other cats and allows the cats to share images of cats to their cat friends. Because ultimately, isn't the internet all about cats? All right, so let's talk a little more about the why, or management. We start off by saying we're going to talk about resources, and that's all hardware. However, fundamentally, the management involves people as well, because other people might be contending for the same resources that you need. Coming to an understanding with the other people involved will likely be very helpful in setting priorities for you and your services. Whatever you're building will likely fall into one of a few buckets. It might be a product, and it will generate some return on investment. Say you're building a photo sharing app, and the product will require a subscription. That subscription, in turn, will cover the costs of the hardware and other resources. Or you're building something that provides a long-term payoff, such as a load balancer or storage system, or some other shared infrastructure. Or your system or feature is experimental. In this case, you'll want a shorter-term plan with other exit criteria. Or finally, your system might be required by law. This might be a system to filter for unlawful images, for example. If the regulations in your jurisdiction say only cats may be uploaded to the internet, then you'll definitely need to filter for non-cat images. And thinking about priority, you'll want to anticipate what happens when your product undergoes a priority change. How to shift resources to emerging systems as they become more popular. Or how to withdraw resources from underused systems or systems with waning periods. Now here's our obligatory image of money spilling unnecessarily from some container. And this is a metaphor for how we need to be careful stewards of the cost of our resources. One way of understanding this responsibility is by looking at the trade-offs. And a rule of thumb for understanding trade-offs is to look at the amount of software engineer time, or SWE hours, that it takes for a programmer to make a change that saves resources. You don't want to spend a week's worth of an engineer's time only to build something that saves a few CPU hours per year. that trade-off is just not worthwhile. However, if you say that it takes a programmer 5 days or 40 SWE hours to make a change that then results in a process running with a 10% increase in efficiency, can you quantify that savings? For example, you'll need to know the cost of CPU seconds in your environment. So that's one of the things that can lead you on the path to more efficient resource management, understanding the fundamental costs for engineering time and resource time, and then you'll be on the path to understanding where you can make trade-offs. And there are other metrics as well. In some cases, it may be very appealing to change out hardware for newer, more efficient hardware. However, in almost every case, this would be a big project with a capital BP. And this is why cloud providers are really good, because they invest in the capital programs to qualify, test, and deploy new hardware, and then virtualize these in a way that you can use for your application or service. After all, changing out hardware often also means changing the software that goes with it. And these might be operating systems, low-level drivers, or updating library code so it can take advantage of new instructions that use the newer hardware more efficiently. And also, swaps are time-consuming and require additional testing. So even though there may be better hardware out there, moving from one generation of hardware to the next can be time-consuming and costly. Now we're going to talk a little bit about design and how you can design your systems effectively to understand their resource usage. A good design will support a system as it grows, and this allows for new efficiency as the software ecosystem evolves. A software ecosystem will usually have a unified control plane, some way of exchanging operational information about the software within the ecosystem, so that upstream components know about downstream components, and everything reports into a central monitoring and logging facility. Without systems that grow or scale or iterate, you'll wind up with software that might be too rigid or hidebound to manage effectively. You might also develop a software ecosystem that doesn't have enough of a shared control plane or a way for different components within the system to exchange information about what they're doing. And this in turn hides some of the operational cost. And by hiding the operational cost, you can't truly understand the resource usage for different parts of the system. Now, the image server that you see on the screen, it can scale pretty effectively. This sample design shows each component as a discrete service. We've got an upload service, we've got a download service, and we've got a search service so that you can find images uploaded, say, by tag or by specific people. And each of these can grow, or we can add capacity independently of the others. So when we put all of these things together, the management, the measurement, and the design, we wind up with the combination of the automated components from the systems that you already have, plus an agreed upon set of priorities that everyone shares, plus a system that has an extensible design. And now you can begin to understand what the system does, explain why it does these things, and know what to do when something changes. So now you're asking yourself, great, where do I start? Well, you can almost certainly pack your software more efficiently. That is, you can stuff a bunch of different and possibly unrelated pieces of software into the same hardware and maximize CPU usage, maximize network usage. It's also important that by doing so, you don't introduce new sources of contention. So you're going to want to have a good set of numbers that you can use to establish a baseline and then inspect the system as you make changes. And for a real-world example, I can tell you about a system I worked on which had almost no CPU usage, very low CPU usage, under 10%, but it used a lot of RAM. In fact, it was maxing out the RAM available on its underlying hardware. What we realized was we could make a trade-off. We could exchange a little bit of CPU and compress the data into and out of memory. So we could put more data into memory at the cost of some CPU cycles. We made that change, and the software was able to grow without actually needing more physical resources for several more years. All right, so now we can dig into the systems that help us gather this data that I've been talking about and look at what these pieces of data can tell us. Instrumentation provided by many application frameworks lets you know how much of these resources, the CPU, network, and memory, that your system or product uses. You can build dashboards from this, and you can aggregate and use the data to analyze system performance. So even though you're collecting and aggregating all this data, interpreting it can be a challenge. Make this easy for yourself. So I encourage you to use the data that you have. And use is a method for building dashboards, and it stands for utilization, saturation, and errors. This provides key fundamental insights into the hardware resources used by your system. And it allows you to make straightforward correlations between the requests that your service receives and the resources used to handle the requests. The dashboard that you see here on the screen is from the service I mentioned a moment ago, where we traded off CPU for better usage of our RAM. Across the top of the right-hand side of the screen, we show the number of requests over time, and then on the bottom, the CPU and memory over that same time interval. And this helped us establish a baseline for the service's healthy operation. And then we were ultimately able to use this data to build models of how the service might grow. And this in turn led us to build capacity plans. Building capacity plans provides another long-lasting perspective on the resource usage of your system. Initially, you may use your experience to guide you. That's what's the guessing part of capacity planning. But over time, really over a short period of time, you'll pull in the instrumentation that your system has and use it to develop profiles and a more nuanced understanding of how your system works. So that's B, the instrumentation. You really don't need any free download from mycapacityplan.com. Ultimately, you need some guesswork, that's your intuition, and some data, that's your experience. And the capacity plan might take the form of a spreadsheet, it might be a YAML file, and whatever form it takes, it should be something that can evolve and something that you can feed into the control plane of your system so that you can then allocate resources based on the capacity plan that you have. And the capacity plan should include both the resources that the service itself uses, as well as fixed costs, because the software exists in an ecosystem, and it will need to have load balancers, proxies, compute resources for async or batch processing, as well as resources for monitoring and logging itself. A capacity plan also allows you to establish guardrails for how many resources the system is allowed to consume. But what we're looking at here is an example software ecosystem. It's a simplified view. It has a metadata service and a single user-facing service for uploading photos. It is an example of a system that has some replicas, as you can see by the multiple boxes for the upload service. And these are new instances created automatically as the load increased on the service. But what's the problem that might happen here? With unbounded ability to grow, we might wind up with hundreds or thousands or millions of servers providing uploads for cat images. And that's great. More cat images are better. However, that would consume a lot of resources. We may not have all those resources, or we may be starving other systems' resources. So what we want, then, is some big red button, or something that we can whack very quickly, whether it's a button on a screen or a command line that we run, that stops the unbounded growth of our system. So you don't want to be able, your Kubernetes system, to create instance upon instance, nor do you want to feed your Java server endless amounts of RAM. You want to be able to have a big red button that says stop, hold things where they are, and gives you time to inspect and debug the service. Another important part of the automatic management of resources within a system is load balancing. And load balancing very simply directs incoming requests to parts of the system that have available resources. But this belies the complexity of many load balancers, which need to understand how much each request costs and whether the available backends have the resources to service that request. And that's where domain-specific load balancers can be extremely useful. By domain-specific load balancer, we mean something that can understand the cost of a request to different parts of your system, and then respond to those by saying, I have capacity for 100 more requests of type Y, I have capacity for 1,000 more requests of type X, I have no capacity whatsoever for requests of type Z. And this kind of load balancing can be a critical part of both distributing load and making efficient use of the resources in your system. You may also need to have multiple levels of load balancers. This diagram on the screen shows that there's a user-facing load balancer which takes the incoming requests and sends them to various middle parts of the system. And then any child requests spawned by that initial request themselves go through internal load balancer that directs the sub-requests to a particular backend. Hey, multiple levels of load balancing mean even better resource usage, because then we can very evenly spread out the incoming requests to many different backends. So this also ties in with the system design. When you can design systems so that you can easily insert additional levels of load balancing, and you can break apart different components into their own services, then you've got a system that can scale and respond to changes in resource management. And now, what's next for you? You can develop a model. Start with a spreadsheet, or perhaps a small program in Python. Write down the constants that you can identify, the cost of a CPU second, how much a SWI hour is. Then add in your variables. How many instances do you need to run? How many user requests do you expect to serve in a given time interval? Employ the use method and these dashboards to see how much CPU your service consumes. You can take all of this and establish a baseline for your service, and then track experiments. What happens when you add a load balancer? When you add a cache? Track and evaluate these experiments. And finally, look to the data to understand your system. Take this data to new generations of your system and consistently improve upon your designs. Thank you. I'm Salim, and I welcome comments and questions either over email or at Twitter.